Good morning. We will wait some minutes in order to let everyone log in inside the webinar. Okay, I think that we can start. Good morning to everyone. Thanks for being here. Let me introduce myself. My name is Andrea Bittasi. I'm an R&D software development supervisor in Marpos, and I am also the leader of a replicability use case inside the IoTwins European project. Today, we will talk about how IoTwins, a big data platform for optimized and replicable industrial and facility management models, can be used to facilitate access to HPC resources and use of big data by SMEs. The IoTwins approach is based on a technological platform allowing a simple and low-cost access to big data analytics and functionality, AI services, and edge cloud infrastructure for the delivery of digital twins in manufacturing and the facility management sectors. We will show today how this approach can be used to generate value-added services through digital twins, services that can then sold to your customers. Let me now introduce you to today's speakers and the webinar agenda. Francesco Millo from Bonfiglioli Riduttori, coordinator of the IoTwins project, will start by presenting the aims and the objectives of the project. It will then be the turn of Daniele Cesini, IT researcher, Alessandro Costantini, researcher engineering, and Cristina Dumma, group leader of distributed systems in the Italian National Institute of Nuclear Physics, will present the product as a service infrastructure that is the goal of the project. Andrea Borghesi, researcher at Alma Mater Studiorum University of Bologna, will then talk to us about machine learning, physical simulation and optimization, and predictive maintenance services based on digital twins generated and obtained thanks to the infrastructure. Finally, Alberto Sita, software designer at Marpos and responsible for the development of the use case that Marpos is implementing in the project, will show us how the product as a service can be used as a facilitator to access high-performance computing resources to create value-added services that can be sold to customers. Let me now pass the floor to Francesco Millo, who will illustrate the aims of the project.
Thank you very much, Andrea, for the nice introduction, and good morning, everybody. Let me share the screen today to discuss introduce the IoTwins project. And I already told you about its title, and actually this is the point that was in our application when we applied for this Horizon 2020 project, was to provide a fully fledged platform for industrial SMEs in order to let small and medium enterprises have proper access to let's say top of the edge technologies, even if maybe this kind of companies don't have the scale to reach very developed technologies. So the goal of the European Commission, while funding this project, was exactly this one: to provide small and medium enterprises with a fully fledged platform, enabling easy and rapid access to heterogeneous cloud HPC-based resources for advanced big data services. This was the ultimate goal. Now, let me enter a little bit more into details, because I know I have only 10 minutes, so I got a rush. This is the idea of our project, so it's very boring if you want, but the key point here is that the project is going to last 3 years. It started in September 2019, and it will be over at the end of August this year. The overall cost, expected cost of this project was roughly 20 million, of which 16.4 are provided by European funding. Okay. Okay. This is our consortium. Usually, when you talk about projects, you start describing the structure of the project, and then maybe you mention partners and so on. But in this case, I think that the ultimate strength of this project really relies on its consortium. Here we have 23 partners coming from 8 different countries, European countries. And if you see, there is a strong bunch of Italian companies belonging to this consortium, Marpos, of course, which is hosting today this webinar, and also Monfilioli, to which I belong, and Università Bologna, INFN, Arter, and Cineca. Now, I should highlight maybe that as Monfilioli, we are coordinator, but no, the key point here that I want to highlight here in this slide is that our partnership is extremely wide and includes very important partners. I mentioned, to let you understand what I mean, that we have 2 supercomputing centers, Cineca in Italy and Barcelona Supercomputing Center in Barcelona. And these are 2 of the 3 most relevant computing centers in Europe. The third one is in Helsinki, Finland. So this was a really important advantage when we applied for this project, because we had the chance to say, you know what, we have the highest computing capacity here in Europe with these 2 partners. Then we have important industrial companies such as Marpos, for example, but also other such as Siemens, Thales, Guala Closure. Maybe you don't know Guala Closure, but if in the evening you have a beer or an Amaro, probably the closure is made by Guala Closure Group, which is a company from Luxembourg City. And then we have also Setem, ESI, Warrant, KK Wind, TT Tech. You see all the list. And you see also a very unusual brand, which is Barcelona Football Club. We'll talk about it later. I know it's a fancy name to have within our consortium. Okay, let's move on. here is what I was mentioning before. So the basic idea of this project, so lowering barriers for SMEs to take up to receive and use advanced technologies in order to optimize processes, increase productivity, potentially also safety, and so on. And again, we see, I said that we have 23 partners. You will see we have also 12 test beds. You will see in this slide, this is the structure of the project. So here we have at the beginning a technological platform that provides services to 7 pilots and also to 5 replicability pilots. Let me explain a little bit better. So I already said that we have a fully fledged platform expected to enable easy and rapid access to heterogeneous cloud HPC based resources for advanced big data services. And this is what is developed in WP2 and 3, the work packages belonging to the technological platform, the one providing as cloud infrastructure, machine learning services, AI services, and digital twin services. Digital twin is an important part of this project, and the name of the project, IoTwins. It's a mix of the word IoT, because we are providing IoT services, and digital twins. So the ultimate result was IoTwins, as I said. So this platform provides top of the edge services to 7 pilots, which are split in 2 areas, manufacturing test beds and facility management test beds. Then once these are over and fully tested, we can move on to the 5 replicability pilots. These replicability pilots have the ultimate goal to show that the solutions we provide with our platform are not just solution specific, industry specific, application specific, but can also apply to other situations, to other similar situations that are not the one initially tested in the 7 pilots. Let me enter a little bit more in the detail in order to understand maybe this concept. So, for example, in the manufacturing test beds, one of our partners is Aguara Closure. So Aguara Closure is the one, as I said, the one providing closures for spirits, and we are testing the solution in their main plant in Luxembourg. Then this is one of the 7 pilots. We will test the same solution in another plant. Well, Closure has 20 plants spread out all over the world with several different product processes. So we can test the same solution in another plant with a different process to verify whether our solution is stable and replicable or not. Similarly, we have also facility management test beds. And now is a moment when I talk about Barcelona Football Club, because Barcelona Football Club is not just a well-renowned football brand. It's also a pretty innovative company. So they have an innovative spin-off named Barcelona Innovation Hub, which is working with us because we are building the digital twin of the Camp Nou, their main stadium, one of the biggest in Europe, hosting up to 100,000 guests and fans. And the goal here is to simulate the crowd flows within the stadium in order to optimize safety issues and also commercial issues. Now, after this pilot, we test the same solution in another stadium, always belonging to Barcelona. Barcelona has more than one stadium in the world. And we test this solution in another stadium to verify whether what we found was actually applicable to all the stadiums, and not just to the one single stadium of Camp Nou. Okay, so this is the basic idea of replicability pilots. Okay. Here there is a more detailed list about each single test bed. I will not invest time on this with one exception, that is Bonfiglioli. I belong to Bonfiglioli, and so let me tell you that we are working with Cake Wind to provide predictive maintenance solution for wind turbines because we are leader in gearboxes for wind turbines. And I know I have only 10 minutes. The 10 minutes are already over. Before ending my short presentation, let me say that yes, Monfilioli is the coordinator, the overall coordinator, but we rely a lot also on University of Bologna, which is the scientific coordinator, so the one having the deep knowledge of the technology we are implementing in our platform. And also we work with B1, which helps in the administrative coordination. Now, time is king and is also over, so I will stop sharing my presentation if I can. Okay, because I know my time is now over. Okay.
Thank you, Francesco.
You're welcome. It seems easy, but I can stop share. Okay.
Okay.
I was able to.
Okay, you stop sharing.
Yeah, I was able indeed.
Let's now see how the solution underlying the IoTwins is implemented, and I pass the floor to Alessandro that will explain how the platform is implemented.
Hi everybody, hi Andrea, all. I just sharing the screen. Let's see if no, not the one. Here is the one. Perfect. Okay, just go up to the first slide. So thank you for this invitation, and let me present you what we did during the project activity within WP2, and in particular WP2 is devoted to the infrastructure and services to be provided to the IoTwins project. Here we have the agenda. I apologize since the beginning to be in rush because the things are many, and we want to present more or less all the activities that we performed in this time. But so let me go to the introduction about WP2 and the objective of WP2 itself. In particular, the requirement collection that we asked to the different test bed that Francesco explained before in the presentation before. And then together with this requirements, we try to define and build what is called the IoTwins framework for let the user and the test bed and the company use those facilities, and then we will finish with let's say quite a simple explicative demo to to see in practice what it means to deploy a service in let's say distributed infrastructure. So first of all, the WP2 objective and goal. WP2 is the package devoted to the infrastructure and the service, as I told you. And the main, let's say, objective was the one that you can see here in the slide. I mean, the identification of the requirement, the selection of the technology to be used and to be provided, and then those, let's say, development mechanism able altogether to, let's say, let the user, the test bed, the people able to manage the digital representation of their physical assets. Before that, we, as I told you, we had to, let's say, collect some requirements from those test beds. And in particular, we collected the requirements related to the needs of the services, the needs of the of the activity, the needs of all test bed that are in the project. Here you can see in the right part of the slide some of those example of let's say the requirements for IoT, edge cloud interface, connectivity, the need of encryption, and so on and so forth. With those requirements, we have been able to analyze those requirements and to, let's say, try to design what is the IoTwins architecture. Here in this picture, you can see the high-level architecture for the IoTwins project. And you can see from the top slide, 3 different layers, which are the IoT, the edge, and the cloud layer with their services. Obviously, all the layer can communicate at the necessity, the need to communicate among them. And moreover, they have to be assessed by a common application layer. You can see the application layer on the bottom on the slide. And the user, to access this application layer, have to be authenticated. But not only the user, but all the workflow have to be in more or less in some way authenticated. And for that reason, we used what is called the authentication service. Together with this, you can find that in the left part of the slide, we just provide some ancillary services as a support of all the layer and that I mentioned so far. Going deeply more in detail, here in this slide, we can see in particular the edge and the IoTwins cloud layer, and some, let's say, aspect of the layer itself, layers that are composed, the connection among the 2 layers, and how access it, or better, them from also administrative point of view. So these are quite complex. And but let me speak about first of all, with this slide, we are going step by step into the details of the different services that we will be able to, let's say, design and focalize. So first of all, the authentication. As I told you, the authentication is one of the most important service because it enables the authentication both from the user side, but both also from the user within the service itself. So for the authentication, we used a service that has been developed within INFN in the past project that is called the Indigo EIN. This is provided by a common endpoint that you can see there, and this service is based on the group activity, on the group authentication. What does it mean? It means then a user can be part of a user testbed project, can be part of a group, and then can be also within a group, can be part of some different subgroups, and he or she will be authorized, authenticated and authorized from the service to perform some action instead of other, to use some service instead of others. Here in the slide, you can see, for example, the subgroups that are the cloud, edge, and storage for the simple storage service. Then I will speak about that during the slide presentation. We prepared also some, let's say, guides for the use of the service itself, and the instructions are within the WP2 channel within the Unibo teams. That is open at the moment, is open only to the people that belongs to the IoTwins project. Let's say now we are going to have an overview of cloud and the edge layer. We have able to see the authentication part. Now we are going more deeply in detail about the service. First of all, we provide as INFN a cloud-based and OpenStack-based cloud for the infrastructure as a service activities. The IaaS or infrastructure as a service is currently available for 7/12 testbeds within IoTwins project. And the different users that have been correctly authenticated and are in the correct group and subgroup, obviously, they can access the endpoint, they can access the dashboard. But in any case, we suggest, and we have suggested since the beginning, that the access is mainly for debugging purposes. Why? Because we provide different service to access the cloud, different, let's say, more user-friendly services to access the cloud capabilities, but not only the cloud capability, also the edge capabilities. For the edge part, so about the edge, we decided to adopt the Apache Mesos tool in order to be used and to give the access to edge resources. Usually, those edge resources are in-house, are hosted in-house by the partner, by all the testbeds. And with Apache Mesos, each partner can rely on two frameworks that comes from Apache Mesos itself, that are Marathon and Chronos. The first for long runnings, to take care of the long running service. The second is taking care about the scheduling of the job itself. So basically, we have currently available 2/12 testbeds are hosted their own edge within the project. Moreover, we have let's say another tenant, a dedicated tenant in the cloud, in the IaaS cloud, devoted for test, basically, which we have deployed an Apache Mesos only devoted for test. Also, in this case, we provide some guides for the partner itself in order to deploy by their own edge. We decided to use the two different, let's say, strategies. One strategy that is all-in-one, in the sense that there is some container-based approach, where the user, the testbed, the partner can deploy its own Apache Mesos using Docker, basically, and container on top of Docker. Or when the resources are more than just one physical server, we provide a guide for multi-node approach using the same way. I mean, using the same container-based approach. Also, the GPU support has been enabled on the edge, on cloud edge Mesos deployment. And for those partners that asked from the requirement that we collected since the beginning, that they cannot provide a public IP, or they don't know, they have a not stable, not known public IP, they provide for them a Mesos VPN solution that is that enable, with this solution, they have been enabled to use, in any case, all the services that we provide using the VPN without having a proper public IP. Here in the slide, you can also see the different dashboard for the services, the Mesos, Chronos, Marathon service, which are completely transparent to the final user. So the final user is not going to see those dashboards. It just is going to see the service that is going to provide all the feature, all the functionality for them. So far we have seen the resources. So far we have seen how we provide those resources and how we provide the authentication for those resources. The problem now is become more interesting because we are trying to understand how to orchestrate such resources in different parts, in different, let's say, provider, in different part of the IoTwins project. And to do that, we use this pass orchestrator. With the pass orchestrator is a let's say, a service that has been developed within by INFN and between INFN collaboration within the Indigo Data Cloud project. Then, time by time, thanks to the activity with the other projects, Deep Hybrid Data Cloud, Extreme Data Cloud, and EOSCAB, this service, this PaaS orchestrators has been enhanced with new feature and new activity, and it allowed to, let's say, provision virtualized compute storage resources on different cloud framework, as well as it enabled to deploy Dockerized service in Mesos within Mesos cluster. The PaaS orchestrator obviously supports the federation among different federated partners and resources, and some scheduling capabilities that enable the scheduling of a service in a resources instead of another, trying also to define a service level agreement for the user itself. Here you can see the architecture of the PaaS orchestrator. You can see in, let's say, highlighted with the blue line, the orchestrator engine that is based on Flowable. You can see, I don't know if you can see my mouse, probably not. Oh, yes. Okay. Probably you can see my mouse.
We can see, yes.
You can see that. Perfect. Thank you. We can, the orchestrator itself rely on some services that you can find here and here. And with those information, it is able to, and also with the so-called adapter or connectors, it is able to understand the, let's say, the situation of the present, the actual situation of the environment, the actual situation and occupancy of the infrastructure, and is able to submit the service to the right resources and to the right provider, obviously. So here we can go more, let's say, deeply in detail with the service layer IoTwins platform. Here you can recognize, okay, here you can recognize the orchestrator, all the microservices that, let's say, are connecting in more or in some way with the orchestrator, and that provide the service provide some important information to the orchestrator itself, and the user is able to access the orchestrator or directly via the API, but we will see in a while, or through a dashboard, a proper web interface dashboard, and the orchestrator is able to submit the service or the job or whatever you are asking, both to the edge or to the cloud. And then those services that are deployed can also in some way communicate among them. How to now we are going to the let's say to the core, to the heart of the presentation, and try to understand how to deploy such resourcing using the PaaS orchestrator. So as I said from the previous slide, we have the orchestrator rely on application program interface, in which the user and both the user and the service can communicate in some way with the orchestrator using those APIs. Using the APIs can be quite tricky, at least for a user point of view. But in any case, all those API and the user and the way on how to use them are quite documented in the highlighted link in the last bullet. In any case, we have been able to provide, let's say, different interface for the final user in order to, let's say, let hide a bit those, let's say, those long command line for using the APIs. And for example, we provided this command line interface client that is called Orkent, that is able to, it is a tool able to dialogate more, for example, with the orchestrator by using a set of quite short and well-known intuitive, let's say, commands for using the command line interface. So using this tool, a user is able to dialogate with the orchestrator and submit what we will see. We will be called in a while Tosca template, but we will see later on what a Tosca template is, in order to submit their service. Step forward has been done with the production of a web interface, the definition of a web interface that is called the IoTwins Orchestrator Dashboard. So basically, here we have a common endpoint to assess for all the test bed to assess the capability of the infrastructure itself for the user. The user has to be authenticated and has to belong to the proper group to be authorized to do something in this dashboard. And in the dashboard, the user can find different buttons. Let's say that here we have those that I'm going to highlight with the mouse are buttons. And those buttons are referred to a proper, let's say, Tosca template that are referred to a proper definition of a service. What the user to do is just press the button within the web interface, enrich the let's say enrich the Tosca template itself with the input information that comes from your application and are quite important for them, and then just submit the request and wait for the service to be up and ready to be used. But let's see a bit more in detail what it means. It means that the user can authenticate to the PASH Orchestrator dashboard. The user can, here in the PASH Orchestrator dashboard, some, let's say, buttons are already provided, are already available for the user to be used. Why? Because basically some other try to define and prepare those customized activity and services, and then they shared those services within the dashboard itself. And the user can select the Tosca template, can enrich the Tosca template, which I remember you, the Tosca template is, let's say, the way on how the service is described. And then the Tosca template can be also enriched by the input file, input parameter provided by the user. The Tosca template enriched is passed to the orchestrator. The orchestrator try to, in some way, just asking the microservices that I presented before, is able to understand where to submit the deployment, cloud instead of the edge node in of the partner, and then submit the service and waiting for the service to be available and usable for the final user. Here we can see the dashboard deployment workflow in a more, let's say, intuitive and extended way. We start from the user. The user is going to be authenticated through the IoTwins Indigo IAM solution service. Then the user is able to choose among a Tosca template already customized or already available for the use of the user want to apply. Then the user can customize, enrich this template by adding some information, and we will see better in the demo how the user can do that. Then after that, the user can submit the job to the orchestrator, and as soon as the job is completed, the deployment is complete, the user can get the endpoint of the service and use the endpoint of the service and the information provided as input to access the service itself. That in this case, and in the case of the demo that I'm going to present right now, is InfluxDB. So let's go into to see a more detailed demo on how to deploy services using within the IoTwins platform using the dashboard. Just going to share again. Okay, you should see the movie. So basically, the user can access the PIS IoTwins dashboard. This is going to be redirected to the authentication service. As you can see here from the slide, the user can choose among different buttons. And in particular, we are going to see how to deploy an InfluxDB server on top of a virtual machine, and better, a Dockerized InfluxDB service on top of a virtual machine. So the user is going to select. Oops, sorry. Okay, the user is going to select the right group to be used for the deployment. In this particular case, is a subgroup of cloud. Then we are going to use the run Docker with the persistent volume button. That is basically that is already prepared and can be customizable with a different kind of application. And this button is enable the user to run Docker on top of a virtual machine with a persistent storage to be used basically. And as you can see here from the presentation, the user is just setting the input that are interesting for them. For example, the volume size, for example, the Docker image to be used, that in this particular case is InfluxDB. Some other things, for example, the tag of the image, if you have a particular tag, for example, or is better to say that in this particular use case in demo, we are using the image provided by Docker Hub. But the user can use their own image, depending on the image, obviously, that is going to use. But let's say generally, it can use both Docker Hub and other hub or personal hub to use for these activities. Then we have to define some port mapping, the port that the application is going to use, the path of the volume, and the port of the service that are going to be open from the cloud point of view. And then in the very last part of the template, the user is able to set some let's say value, some variable intended as a key and value, basically, that are proper of the application itself. In this particular case, we are providing InfluxDB, and then the user is setting username, password, init mode for InfluxDB, and so on and so forth. So all the variables that InfluxDB required to be used, basically. After that, we can see from the movie that the user is going in the advanced part of the template, and here before submitting, the user can or let the orchestrator submit to choose the proper provider and submit the service for them, or choose among a list of available providers. That is up to the user, obviously. And then after that, the user just submit the request, and this request is going to be elaborated by the orchestrator, the pass orchestrator. And as soon as the deployment is complete, the user can access all the information that he or she provided since the beginning. Here, for example, you see a list of the input value provided by the user during let's say, the initialization phase, but also the output values that can be used by the user to reach the proper endpoint and to reach the service at the endpoint that we defined. In particular, we are using the node IP, that is a public IP in this case. So the user can access the service that is InfluxDB. I'm going to remember you that is InfluxDB. Just put in the variable that have been defined. If you don't remember the variable, you can always go to the dashboard and see the variable that you set. And then here we have a fully functional InfluxDB server that can be used by the user. So just to point out this, just to point out that the user has the possibility also to log in to the virtual machine that has been deployed and where the containerized InfluxDB service is running. But why? Because basically just to for emergency reason, if the service is not going to respond or there is some problem with the service itself. So, and this possibility has been provided because here you can see a private key that can be downloaded, and then with this private key you can access via SSH. You can log in to the virtual machine and see what happened and try to resolve the problem. So I'm just come back to the slides. Let's see. No.
You're not in presentation mode, Alessandro.
Yes, I'm going to redefine the presentation mode. Okay, I should be there now.
Yeah.
Perfect. So after this demo, just let's say, let me give you some other details about the services that we have been able, WP2 has been able to provide to the IoTwins service. For example, here we have the data transfer via this service that is MinIO, that is called the MinIO, which support the simple storage service. In particular, we provide for all the test bed that required the service, we provide the proper endpoint, and obviously we provide for those services the possibility to store their data for the test bed, providing two different interfaces, the web interfaces available for each single test bed, and also a Linux client interface to be accessed by the command line to the data in their bucket, using obviously the S3 approach. And then few words about the customization. As far we have seen from the template, from the demo, something that has been already, let's say, customized and prepared for the scope. And but basically those templates, those buttons that are available from the web interface can be customized by the user with the help of the developer usually. because basically what we are using is, as I told you from the beginning, is the Tosca template. Those Tosca template, the acronym Tosca is the acronym of the OASIS topology and orchestration specification for cloud application. And this is an OASIS standard language that describe services, service component and their relationship. And this is used to enhance the portability of the service itself, both in the cloud environment, but also in other kind of environment, for example, Mesos. And as you can see from the slide, the Tosca is, let's say, divided in different parts. We have, for example, the custom type selection and definition. Here we have a collection of what are called the node type. A node type is something that defines the component and their implementation. Then we have the input part that can be customized by the user. Then we have the selection of the proper custom type imported in this let's say, in this step. And here we can also use just a single custom type or a workflow of activity of custom type to be used. And then we have also the output that is get from the deployment itself. How those part works? So basically, the Tosca template, as I told you, can be customized from the user, from the needs of the user. Obviously, is the better situation is having a custom type already prepared and used. And for those reasons, we let's say we propose the sharing model, in the sense that if something is a custom type that has been prepared, we are trying to, let's say, promote the sharing of those custom types. But if not present, or the custom type can be defined, can be structured, can be also modified from a actual custom type already available. And those custom type rely on the Ansible role. And the Ansible role basically is something that is able to define all the steps for a service to be up and running, installation process, and so on and so forth. And as Docker Hub is the hub for the images, Galaxy is the hub for the Ansible role. And when you can, and when you're trying to define a new custom type, you have also to, let's say, to define a Ansible. Oops, sorry. You have also to define an Ansible role for that custom type. Also, in this case, you can reuse the Ansible role that are made available for the community, for the Galaxy community. But if they are not present, you can build your own Ansible role. You can define your own Ansible role, and with this, you can define your own custom type to be used within the Tosca template. And all this activity, at the end, are summarized in the definition of the button that the user can press and submit its own service. So okay. Sorry to bore you with this activity, with this explanation, with the presentation, the services that WP2 provided for the project. And I'm at the end of my presentation, and I thank you thanks first of all, Andrea, for the invitation, and all of you to be present. Thank you.
We are a little bit late, so I kindly ask to everyone to keep the question for the end. Now, thank you, Alessandro, for having shown us the implementation of the platform that allow the deployment and the orchestration of services. But one of the main points of IoTwins is that services are not only storage or authorization or secret skipping or something like that, but mainly in the IoTwins project are also the algorithms that are used to optimize, to use machine learning techniques to have the possibility to use the big data collected from the IoT in order to obtain new services and innovative added value services. So let us switch to the presentation of Andrea Borghesi that will show us the artificial intelligence algorithm that has been used in the test beds in order to obtain these results.
Good morning, everyone. Thank you, Andrea. I'm Andrea Borghesi, an assistant professor at the University of Bologna, and I'm very sorry that today my webcam decided not to collaborate, so you won't be able to see my face. But if you search for Andrea Borghesi on Google, University of Bologna, there is only me. So let's move on now. I wanted to give you a quick overview of the AI-based, artificial intelligence-based services that were developed for the IoTwins partners in the IoTwins project, as Andrea was referring to earlier. And I want to stress out that while we have just seen how the platform is built, how all the pieces, all the components of the infrastructure of the platform work in collaboration. Here now I will present you a few examples, let's say I will show you briefly the overall list of the artificial intelligence-based services, and then I will focus on three specific use cases to give you more of a hint, to give you more of an idea of how these AI-based services are used. What I want to stress out is that in this case, artificial intelligence has been chosen as a let's say a family of tools, a family of software components that can really help system administrator and industrial facility owner and whatsoever. Why artificial intelligence in this case was really helpful? The key is that with this Industry 4.0 development in the last few from 5 to 6 years, we have been starting to collect huge amount of data. And when you have a lot of data which characterize your system, which characterize your machines or set of machines or any kind of complex system such as an industrial plant or a stadium, for example, then once you have such a big amount of data, the key challenge is to extract information from this data and to build a model that rely on this data to forecast the behavior of your machine in the future, and at the same time to take decision thanks to the prediction that you can make with the models. So to build this digital twin, we decided to adopt three main types of artificial intelligence-based models. On one hand, we started with machine and deep learning models because we had this huge amount of data available, and machine and deep learning model are really suited to extract information, to get insight from a large amount of data. However, we realized it at the beginning, before submitting the project, so it was not something new, but we knew that even with all the data that you can collect from a live up and running system, you might not have all the data that can be useful to build a digital twin. For example, when you deal with anomaly detection or fault identification in real industrial systems, it's very rare having faults or having components that break down. Not in all cases, but in some cases, it's very rare to have faults, at least in the lifetime of a European project, which is between 2 and 3 years. So what can be done in this case? One, if you don't have enough information coming from your data, another idea is, can you simulate the behavior of your system using simulation models? And this is what we have done using exactly simulation models. Finally, once you have prediction, once you have simulation, so once you have a proper understanding of your model, the next step is to build optimization models that allows you to take decisions. So once you know how to characterize the behavior of the system, you also need to know how to take action based on the simulation results, based on the prediction made by data-driven models and so on. And for this, we implemented optimization models. Just to be very, very quick, because I get that I think that you got the point already. The main idea of the AI-based services is to extract value from the facility, from the data collected from the facility, collect this data, collect this value, and combine it in a smart way to extract even more value. And this is something that as AI expert, we have been doing, at least at the university and the research institution in the last 10 to 15 years. The point is that there is generally a gap between AI expert and the expert in the industrial domain. So facility manager, small, medium enterprise owners, and so on. And the main idea that we have here in IoTwins is to bridge the gap between AI expert and, let's say, domain expert. And this is the reason why we develop these services as a list of services after having collected all the requirements from the variety of partners that Francesco has introduced at the beginning. Once we have this variety of general services, then the second idea was to provide support for the testbed to actually ground these services on their specific testbed. I want to quickly point out that the services that we have been developing, the machine learning services, the optimization service, and so on, have been devised to be deployed both on the cloud and high performance computing infrastructure and on the edge. IoT devices in general do not have sufficient computational power to run the AI-based services, and in general, all the services has been provided as containers, Docker containers, and this has been done to simplify as much as possible their handling by the IoTwins platform that was described earlier. We have used a conjunction of open source and proprietary tool. For example, most of the machine learning models have been developed using only open source tools, and they can be then published, and they can be, the code of these open source services can be made public. At the same time, for example, in the case of simulations services, we have been relying as well on proprietary tools. So not everything will be made fully public after the end of the project, but I would say that the vast majority of the services will be made public at the end of the project. And in general, the services are all reusable because they have been identified after having a lot of discussion with the testbed partners to cover their most frequent need. So many partners have probably they have very, very similar needs. For example, anomaly detection or failure prediction. Those are needs that are common among different type of industrial situation, industrial context. And the services at the moment are being hosted in a GitLab repository internal of the project, but for example, this is the view of part of the services. I mean, this list, if you're able to scroll down, goes down quite a lot, and they will be made public, at least a significant fraction of them by the end of the project. Just to give you an idea about what kind of data we've been collecting. We have been collecting data from very, very heterogeneous systems, so ranging from a large-scale facility to industrial platform to stadiums. In general, all these heterogeneous data has been stored as time series with multivariable, and this is on one hand hard because doing time series analysis, when especially the time series is a very high dimension, is a very complicated task using statistical tools, but is also a very, very good thing for deep learning and machine learning model because they really can exploit, they can extract a lot of information from time series data. And I don't want to bother you, to bore you too much with, let's say, high-level details. We have plenty of detail in documents and whatever. By the way, if you go at this YouTube link here, you can see an example of the actual services deployed. So this is not just, let's say, empty talk, but we actually have deployed and tested these services, and you can see some simple example here at this website, at this YouTube page. But I don't want to give you too many details.
Andrea, can you copy it and put it on the chat?
I think I can. I definitely think. Let me do this. I definitely can. Thank you, Andrea. I will stop the sharing screen for 1 second. I will send it to everyone, and it's now on the chat. Thank you, Andrea. I go back.
Perfect. Thank you.
Oh, thank you. Very smart. Okay, back to the presentation. Since we have tens of different services, there is no reason, I think, to give you details on each of them. I want to give you an example on how they are actually been deployed on already deployed use cases, and one use cases that we are still working on, but we are confident that will be completed in the next couple of months, let's say. So a very common problem for industrial components and industrial machinery in general is to estimate, predict when your components will break. So estimating the remaining useful life. And this is a very complicated but widespread problem, and in general has been addressed in from many different angles. In this case, we decided to devise a machine learning model, and in particular, we employed a temporal convolutional network, a type of neural network, which is let's say a type of deep learning model which strongly relies on the availability of a lot of data and the possibility to train your model using a sophisticated computational resources such as GPU. And this is the general scheme of the approach of the deployment of the testbed that we have. And this is in particular related to the Guala closure testbed, the number 4 that Francesco was saying earlier. We collect the data from this testbed, and this testbed basically it refers to identify the abnormal wear of beer coating for an industrial plant. This is the molding machine that we are monitoring. These are the integrated sensor, and we are collecting many different kind of features that characterize the behavior of this system. And once we have all this data, we send it to a high performance computing infrastructure. This is M100, and it's part of Cineca supercomputing facility. With this data, we then train a machine learning model, and in particular a temporal convolutional network, which is then used to make live inference, to make prediction on the live data. And this has been tested and deployed. So after the training and after the validation, these are the results. I mean, we are still working on this. We are refining now the results. We're trying to improve the precision of the machine learning model by collecting even more data. But this is what can be seen from the GCL perspective. So the end user. Those are a series of features that characterize the system behavior, and those are live monitoring, live view of the data from the molding machine. And this red line identifying an anomaly. And here we can see instead the actual remaining useful life prediction. And you can see this is a normalized number, so don't expect to see minutes or hours, but I just want to point out that when the anomaly emerges, when the anomaly arises, we have a corresponding decrease in the remaining useful life. This means that the machine learning model is actually capable of anticipating the insurgency of an anomaly. In a similar fashion, we also worked on data center, and in particular on testbed number 6, we have Cineca as a partner, and we have instrumented all the supercomputing facility of Cineca using a tool called Hexamon. And once we have obtained all the data, all the information coming from the Hexamon system, which describe in a very fine-grained detail all the components of the supercomputing. So the computing rack, the status of the storage system, the status of the core, the computing components, the status of the GPUs in this system, the status of the connection. We collect, for example, for each computing node, more or less 200 different metrics. And you have to imagine that in a supercomputing center, you have thousands of nodes. So we have plenty of data coming in from every second from our system. Once we have all this data collected via the Hexamon infrastructure, which is part as well of the IoTwins end results, we obtain a very fine-grained and detailed digital twin. And in this case, the idea was to perform anomaly detection, so automatically identify when a problem was present in one of the computing nodes of the machine. And in this case, we employ another type of deep learning model, which is called autoencoder, which is very, very well suited for dealing with this kind of anomaly detection problem. We have done it, and we keep on working on this, and we try to refine this autoencoder model that you can see here by attaching it as well to additional let's say a fine-tuned component that not only detect an anomaly, but allow us also to predict in advance when the component is going to break. This is a slightly different approach to remaining useful life estimation, but conceptually is similar, is comparable. And in this case as well, you obtain pretty good results. For example, you can see here, these are, okay, not live data. This is an image taken from offline results. And you can see here that on the x-axis, we have the time. On the y-axis, we have the anomaly signal. So the blue line refers to the actual anomaly, right? Here, this blue little dotted line is the presence of the anomaly when we have anomaly signal to 1, and when the anomaly signal is to 0, we have no anomaly, no failure. And in this case, we see that our deep learning model, which is a combination of an autoencoder with a couple of supervised layers, in this case, the autoencoder is starting to get a bit antsy, to get a bit nervous even before the insurgency of the anomaly. You can see that the yellow line is the prediction of the actual deep learning model. You can see that the yellow line completely mimic the blue line, so it completely detects the fact that a problem was present in real time. But additionally, it can also see that something strange is going on even before the insurgency of the anomaly. And we managed to obtain an average anticipation around between 40 minutes and 1 hour and a half. So on average, 1 hour and a few minutes of anticipation. And these are, I want to stress out, 2 successful testbeds that have been already developed, fully deployed, and are still under ongoing validation, but we have already pretty significant results. Finally, a couple of ideas of what I've been working, especially in collaboration with Marcos. In this case, the idea was to, let's say, obtain machine learning and artificial intelligence-based model for the industrial processes happening on automotive engines. And in this case, we have collected data from in production manufacturing line for automotive engines in the industry, as it's again a time series with multiple variables. And in this case, we had a couple of different goals, but we can simplify them, stating that we wanted to analyze faulty behavior and critical situation and distinguish between different type of manufacturing processes. And in this case as well, we deployed and we developed and we are still deploying now a set of deep learning models, once for each specific goal that we had in mind, and they are based on historical data. And this model, of course, has been trained using the sufficient amount of computational capability provided by the GPU within the project, within the consortium. And in particular, we had three types of different services: multivariate time series classification, multivariate time series data augmentation, and anomaly detection as well. To give you a bit of more detail, but I'm going to be pretty quick, this is a supervised approach. So in this case, we expect the data to be annotated. So for each time point corresponding to a time sample in our time series, we need to know if it corresponds to a normal state or anomalous state, or if it corresponds, or if entire time series correspond to normal processes or processes of one type or another type. And once we have this kind of data, so annotated time series information, we can apply many methods. And the one that we find to be more suitable, because it's a nice balance, a nice trade-off between the complexity of the model itself, so its capability of being executed on the edge without too much, let's say, computational requirements, while at the same time maintaining a high accuracy, was the convolutional neural network, one-dimensional convolutional neural network in particular, which exploit the temporal locality. So it's a type of network which is very well suited to work with time series. Convolutional networks are also used for image classification. In the case of image classification, we are dealing with the two-dimensional grid data, and in that case, so we are using two-dimensional convolutional network. With time series, one-dimensional are fine. At the same time, we also have extended then the convolutional network that was started, its deployment, its development has begun to do time series classification, so distinguish different processes. We also extended it to do anomaly detection, so distinguish between time series that correspond to normal, healthy industrial process, to distinguish them from faulty industrial process. And this is a variation of the convolutional neural network. And also, since in general, time series anomaly detection requires to have labeled data, and it requires to be shown many, as much as possible, historical processes, both healthy and faulty, to be really, really accurate. Clearly, having faulty processes is very more rare, is much, much rarer, because faulty processes, by definition, we try not to have them. We employ another algorithm which does data augmentation that generates synthetic data. And this is allow us to obtain a much more well-balanced data set to be then used to train the deep learning model, the convolutional neural network, for doing the anomaly detection part on the time series. And I could have many more details to give you, but I guess the time is scarce. So I thank you for your attention, everyone, and I conclude.
Thank you very much, Andrea. We have a question from Cosimo. I think it is related to the first of the two prediction model. So the question is, do you have false alarms? What is the reliability of the prediction? I think it is.
Yeah, that's a perfect question. I think I can anticipate it. We, if you mean in the case, I mean, in the data center case, anomaly detection, we did have false alarm, but I want to, in the data center case, false alarm are very, very bad, and especially in the anomaly detection part, because since the system is composed by thousands of nodes, false alarm might require a lot of useless effort by the system administrator. So we were very, very careful in using what is called a loss function for the neural network to minimize the false alarm. So in general, what we do in machine learning model is not to just maximize a simple accuracy, because everyone in this setting know that simple accuracy is not really so informative. What we do is we try to minimize the false alarm minimize the false negative, and in general, we employ the F1 score as accuracy metric to be minimized. So we did have a few false alarm, but really a small number. In terms of, instead, in the case of the remaining useful life estimation, in this case, we had a larger amount of false alarm, and we are, to be honest, still working on this issue. If I have to be completely honest, we had a few ideas why we are having this false alarm, but I would prefer to have a, let's say, a couple of months more to finalize the validation. It's not I mean, do not expect that we are receiving false alarm every 10 minutes or even every day, but we have faced let's say, bi-weekly generation of false alarm. So this is still work to be done. It's not a perfect machine. It's not a perfect system, of course. You need a lot of data, annotated data, which is very costly. And we hope to continue working on this area to refine this model. I mean, GCL has a lot of interest in refining this model, so we plan to keep this collaboration, continue this collaboration. But still, false alarm, we know they are an issue, and we are working to fix exactly this issue. I hope I answered satisfyingly.
I think you have satisfied. Thank you very much.
Thank you.
And yes, Cosimo say yes, thanks. So you have reached the goal. Now we have seen how to deploy tasks on the PaaS infrastructure, how to orchestrate them both on the cloud, for example, to train AI services, and on the edge, for example, to use the services for doing the inference. But till now we have seen how to use them manually. Now Alberto will show us how it is possible to put all these together in order to use the product as a service in order to be able to sell services to customers using a software as a services approach. So how to use the IoTwins PaaS in order to be able to use the services created by IoTwins in order to take advantage of the data collected and to take advantage of the cloud resources, the high-performance computing resources available on the cloud. Please, Alberto.
Hello, everyone. Thanks, Andrea. I'm Alberto Sita. I'm the software developer behind Marpos Testbed 12. So, as Andrea just said, we are going to introduce our testbed and to talk about how we faced some challenges of the implementation. So let's directly start introducing the background of our testbed. We started from a real plant scenario coming from one of our OEM. In this scenario, we had almost 100 machines divided, as you can see in the slide, and we were collecting through our Marpos Junior modular system different information about the measurement and operation that machine were doing. Especially, we acquired information about the axial torque or the spindle measurement or the vibration. And all of these measurements were done with a 100 Hertz sample rate. And the volume of data was about 1 gigabit, 800 megabit a day for each machine. So this was the main scenario that we take as a starting point. Now I want to share with you a quick presentation of our Marpos Junior modular system. It's a quick video that illustrates how our IoT system acquires and manages data.
Fully automatic tool breakage detection and process monitoring for turning processes with Genio Modular from Artis. Genio Modular is ideally suited for middle-sized and large series. The system has a modular structure. The numeric control captures digital process data and transmits them to the evaluation unit. Various sensors with the according measuring transducers complete the system. The visualization software as part of the package displays the processes clearly.
So we can stop here. So you can have a quick idea of how our tools acquires the data from the machines. So how we can exploit the value of such data? This is our main question for the testbed. We imagine to realize two services. We want to provide new software to complement our devices, and we imagine to realize a machine configuration fine-tuning service with the support of AI, and also a semi-supervised anomaly detection service based also on neural networks. So the main objective of our testbed is to use and test the IoTwin platform that was shown before to demonstrate that innovative technologies such as deep neural networks and HPC resources can be employed to build and release a commercial software that can be used by our customer in a pay-per-use software as a service model. We collaborate in the implementation with INFN and also Cineca that help us during the implementation. So this is our main objective, but what challenges do we face? Some question that arise was this one. How we can manage all the data that machine produced, how we can manage security, data separation, and confidentiality, how we can orchestrate and secure this data flow, and also how we can use artificial intelligence to improve the process control limits of our machines, how we can orchestrate this kind of service directly onto our on-premises resources, and also how can we overcome the barriers and build a computational continuum for our customers, how the deployment can be done. These are some of many more questions that we take into account during the actual implementation. For solving this problem, it is very handy the IoTwins main general architecture. IoTwins offers a first part for acquiring, securing, and storing directly to cloud resources the data coming from our IoT system. Then the data can be accessed by cloud services for realizing AI services. In this case, we can do and perform training of neural networks directly onto cloud resources. More services are offered, like agent-based simulation and physics model simulation. This is a general overview of the service. We used only a portion of that are suited for our objective. Then, one strong point of the IoTwins platform is the ability to communicate back with the edge nodes, enabling an hybrid cloud environment for deploying directly the services onto the edge premises. Then the deployed services can be done for actuating actions directly onto our IoT devices, or also for performing some maintenance and anomaly detection operation directly on plant facility. This is the main architecture that we need to keep in mind during the rest of the presentation. So IoTwins also offers some main building blocks that are the enabling technologies. In testbed 12 of Marpos, we use the technology for the infrastructure and orchestration based on OpenStack and Indigo Data Cloud. We use the technology for managing our software through Docker containers. We already see these names during the presentation of INFN before. We also use technologies for managing identity and secrets management, because it's very important to maintain information coming from our customers secure. And also technologies for data storage, both at the edge and in cloud. With all this technology, we built our demonstrator. Now we can move on our solution, that is a software as a service solution based onto a web portal. Through this portal, our customer can access some service based onto the IoTwin platform, can purchase the service, activate them, and use them to streamline its planned production. We are going now to have a technical insight on how we manage the data upload from the edge premises to the cloud, how we implemented also the machine configuration software and also the anomaly detection service. For the data upload part, we need to keep in mind this main problem: how we can manage the ingestion, how we can manage security and data separation, and how can we orchestrate all of this in a centralized way. IoTwins is very smart in this because enables the security management at the edge node. So the data leaves the plant premises already anonymized and secure, and it's ready to be stored directly in cloud resources that are kept separated between different users. So the data is safe and protected. Our solution is based onto the Genure modular system that is linked to our edge resources. So data are extracted from our IoT system and then published on the edge node that is provided with a message broker that acts like a distribution center of information. This is our main part for data acquisition. From this scenario, we use the IoTwin platform to deploy a pay-per-use service that performs the anonymization and the encryption of the data, and then uploads the data directly onto a database that is InfluxDB, that is hosted in cloud. So here you can see the general idea. The users interacts with our software as a service solution. It authenticates and purchases the portal. Our web service interacts then with the IoTwins platform, submitting a Tosca templates and managing secrets, the identity, and all the orchestration part. So everything is managed from our portal. Then when the service for data upload is ready, it is deployed directly onto the edge premise of the client. So all of this is secured and managed by the platform of IoTwins, using the orchestration via Indigo platform as a service and Tosca templates. Now I'm going to present a short demo on how this works and how it is implemented in a web service. Here we are inside our environment. you can see that the user can interact with this form. The user can select the edge resource, the genres that will be enabled, and also how to upload the data. There is also a clear indication of the cost, and then the user can purchase and activate the service. Here, the platform is communicating with the IoTwins ecosystem for submitting and activating the service. Here we can see that the deployment is on progress. When the deployment is done, all the information are updated, and it's deployed on the edge. Here, there is the Mesos framework on the edge. So you can see that the URL of the services are local, because here we are inside the management part of the edge resource. We can see that the anonymization and upload services are correctly activated and running. We can also have some details about how the Mesos and Marathon stack activates and manages the service via Docker containers. So you can have all the details about the configuration of the single service. Data are then published onto the message broker, RabbitMQ. So when the machine is working, I can see that the data is published and anonymized and uploaded directly onto the cloud instance of InfluxDB. Here we can see that in the cloud instance of InfluxDB, the data are correctly being stored. You can see that signals are stored in an anonymized way, so it's not in clear and it's protected. Moving forward, the data are stored in cloud, and now we need to implement the service. For example, the machine configuration fine-tuning. So how can we exploit the data with an artificial intelligence service in order to improve the configuration of the machine? And how can we use the orchestration provided from the IoTwins framework to do that? Our goal is to realize a service that can be used to optimize the research of the correct control limits, and also to improve the machine configuration in order to streamline the production. We see these benefits from the IoTwins solution. The training can be automatized via the cloud resources. The user knowledge is less relevant than before, because we can use an anomaly, we can use an AI model to infer the experience from the data. And we also can build a continuous computational flow from the IoT to cloud in order to perform this kind of activity directly on cloud. So, having a look at the main reference, we are going to use the modules that can train the network, download then the network and configuration onto the edge node in order to perform an IoT management operation, that is the updating of the configuration. So looking at our implementation, the user will log in and purchase the service. The request is passed to the IoTwins platform that secures a data access that is consistent with the identity of the user. So data are accessed in a secure way. Also, a Tosca template is submitted to the Indigo pass in order to perform the orchestration of the training of the neural network through the data labeling and also validation of the model. When this action is finished, the user can select the configuration directly through our software as a service solution and can select to deploy the configuration directly on edge resources. So a transparent download takes place. And our software can use this configuration to update the configuration onto the specific machine. So the platform as a service approach in this case is used also to retroact onto the system and to apply a configuration on the machine. I'm going to show a quick demo of this service. So here you can see the simulation section. The user can select all the parameters. Here you can see a description, how the data are accessed, the model of the neural network selected, which edge and machine and process. The user can input all these parameters and see how much it will cost. Here, the system is activating the service. We can see that the Indigo infrastructure accepts the request and try to deploy the service. So the training of the neural networks takes some time. So here we are waiting for the completion of the system. When the system will complete, we will see that inside Indigo, everything is done properly. And in our portal, we can see that the deployment is complete. And all the information will appear here in a graphical way. So we can see that we perform different tests on different neural networks. And we can select the one with the best accuracy. Here we can also see the details of the simulation and the performance of the neural network. We can also have a deeper look at the specific details of single neural networks that were trained. And also on how the settings were applied. Now we are going to see how this can be deployed onto our customer premise. Here, the deployment is taking place. So on the local agent, this agent is running inside our edge resource. Is taking place the download of the configuration. we are going to see that the information will be downloaded right here. So the customer can download transparently the configuration. Moving forward, the last service is related to anomaly detection. So how we can implement anomaly detection with the semi-supervised artificial intelligence? Our goal is to save time and money in order to predict faulty event of the line. So we want to use a multivariate anomaly detection to predict this event in order to cut cost and save time. IoTwins is very handy for this problem because it offers an AI-based catalog, a platform as a service approach that we already see. So this approach can be also used in this case to deploy the service directly on edge node. And also the platform enables the storage of big data for also further analytics besides the anomaly detection goal. So here again, we are using the module that enables us to train network and deploys them on edge nodes. Our implementation in this case is very similar to the previous. The user purchased the service. The data are accessed in a secure way, and everything related to the training and data labeling of the anomaly detection model takes place on cloud resources. Automatically, when the service will be ready, the platform will deploy it automatically on the edge premises. So the anomaly detection service will run transparently onto our edge resources. And a local HMI can be installed in order to see what's happening on premises. A short demo. We are going to see here a short demo. So in the third section, the user can activate the service in a similar way like the service before shown. Here we are selecting a machine, a specific tool to be checked for anomaly detection, and we choose also to perform the training of the model. We can select also the data range of the input data for training. Here we are using our historical data of the plant. I can move forward. When the deployment is done, you can see that both cloud activity and edge activity is activated correctly by Indigo. So the model is trained on the cloud first and then activated onto the edge. Here you can see that the prediction model can predict if entry is good or bad. During machine processing, we are able to access the data and to pass them to the neural network that can predict if something is good or bad. In this case, everything is fine. We can wait a second and we can see that if the machine stops, I think it's almost there. Okay, if we stop the machine, sensors are not operating well, so the data is very different from the one before, and the network appears to work properly because it said it is not a good data. So wrapping up all our experience, we think that IoTwins platform is an enabler of a new pervasive business model. The hybrid cloud approach bridges the gap between customer plants and cloud resources So it is a fully automated platform that can be used also in cloud and edge resources. A new kind of approach can be used to build new services that can run on customer edges with a pay-per-use model. Also, the on-premises exploitation of AE models is possible because services are directly activated and used on edge premises. HPC cloud resources are very important because it enables the training of the model in a reasonable amount of time. And also the approach of security by design, scalability, and flexibility is very important for us because we need to guarantee that data confidentiality and separation is guaranteed by the platform. And also being based on open source technologies is a very good point for also future extendability. Our solution is at TRL 4. IoTwins is for the time being at TRL 5. Thank you very much. And now we can have a short Q&A session.
Thank you, Alberto. We are a bit late, so we have seen the concept of the platform, the kind of AI services that has been implemented in the project, and Alberto showed us how all these things can be put to can be used in order to create innovative services that allow to final customer the possibility to exploit the use of the data that are generated by the in the plant, and how the IoTwins platform can be used to deploy, organize, orchestrate tasks on both the cloud and the edge. This allows us to implement a SaaS solution that allows us to sell services on a pay-per-use model. So we can allow our customer to select which are the IoT that must send data to the cloud, store data on the cloud, and on the data collected on the cloud, how this data can be used in order to keep advantage of the IoTwin features. We have other 10 minutes. If any question, please raise your hand on, so I will give you the microphone. Okay, no question, no hands raised. Thank you to all of you for being here with us. I hope this presentation was clear enough to explain the IoTwin platforms, the idea, the concept, and the possibility that it offers to us in order to implement such kind of innovative services. Thank you. And the webinar has been registered, and I will send you the link just in case you need to review something. Thanks to all the speakers for being here and to share with us their experience. I think that we can close the webinar. Thank you. Have a good day.
Bye.
Thank you.
Bye, everyone.
Thank you, everybody.
Bye-bye.
Bye.